This video will actually do with a certain random stuffs that I find that is pretty useful after a certain lecture. Alright, is that the strain displacement relationship, alright, is something that is always being used throughout many derivations for many stiffness matrix. Alright, so if you still remember, the strain displacement matrix or whatever is in terms of the n over your dx, correct? And then you change it as a dn over dc over dx, where this is your Jacobian. Alright, so in furthermore, in other shapes, you'll still see Jacobian in a different way, in a many complex ways and things like that. So the strain displacement relationship is a very powerful thing to model any other shapes at all, because still remember you have an n are your shape functions. Alright, so if you think about it, the n, alright, is it deals with the shape functions of in a different domain. If you still remember, you have a certain displacement in the u domain, and we use interpolation to change to the x domain. Alright, and then we use the x domain to do certain interpolation to change to a curl C domain. Still remember? So imagine, so if you think about it, this is the u, this is a 3D system. Alright, this is the u domain, alright, because it's u, and then you change to a x domain. Think about it, it becomes a x. Alright, so you use the interpolation method, linear interpolation, alright, that you change the u into x. Alright, next, after you change the u into x, alright, then you change the x, alright, this is the x domain, you change it to the curl C domain. Alright, so that the computer can read. Normally we want to change it into this form. Okay, this is often the case for many different shapes, because in a computer normally they will want to represent things in terms of this domain. Alright, where this domain, if you think about it, this shape is a square. Alright, so normally if you want to model any other stuff, any other shapes, you want it to be as squarish as possible. The aspect ratio is very important. Alright, the aspect ratios is with regards to the length, alright, this length over here divided by this length over here. Alright, or maybe L1 divided by L2. Alright, if L1 is equals to L2 is equals to 1, L1 over L2 is equals to 1, this means that it's really a good model to model. But often if you see inside whenever you design whatever abacus or whatever, alright, this often isn't the case, right? Because this often isn't this type of shapes. It can be a quadrilateral, can be a triangle and everything. Alright, so therefore whenever you talk about it, you're going to talk about the aspect ratio between this length and this length. And nonetheless, I may be wrong saying that it may be this length and this length. Okay lah, I think I'm correct lah. Okay, after searching through the Googles, you can search Google for aspect ratio, square and whatever. You can see something like a 2:1. Alright, so this one is like a 2, this one is like a 1, and then so is 2:1, whatever lah. But anyway, at least you get to see that the strain displacement relationship is a very powerful thing that also deals with the Jacobian, because Jacobian helps you to change from the x domain into the curl C domain so that you can read inside the computer, things like that. Okay, and that for when you model a certain model, alright, for example, if you have a certain plate over here, you want to model it by square, alright, this is one of the element, so each element has to be this square, so this thing is considered one element, and then you're going to have another element and another element, so you want it to be as squarish as possible. Alright, if you have a very distorted shape, for example, like this, alright, you have a very sharp angle over here, this is an acute, I think, and this is an obtuse angle. You have a very large acute and obtuse angle. Alright, so this is a very inaccurate model to model. So normally when you see this type of shapes that is coming out in your mesh, alright, then you're going to remesh your stuff such that your quadrilateral should be as squarish as possible. Alright, so that it can actually maintain the aspect ratio as 1. Alright, L1 divided by L2 is equals to 1. So you want the aspect ratio to be as closest to the squarish as possible. Alright, so please take note that every time when you see those types of very distorted quadrilaterals, alright, then you're gonna know that it's not very good, and then you need to remodel again, alright, things like that. What is the criteria is that if let's say you have this thing over here, you have to maintain it as 90 degrees, alright. If we have like about 60 degrees, for example, how should I draw? I also don't know how to draw. Maybe you have an angle that is about 60 degrees, okay, then this is the last warning, alright. If you have lesser than 60 degrees, maybe like 45, things like that, then you are starting to have a distorted shape, so your reading in the abacus will be wrong. So normally when you do your abacus or your computational software, take note that the quadrilateral shape is very important. Ensure that it is as squarish as possible, okay. And yeah, so normally when you talk about meshing, alright, this is one type of element, alright. If you think about this, is actually one of the C is equals to 1, this is C equals to -1, this is another curve C, and things like that, alright. Normally if you were to have a force that is pulling in this direction, or in the tensile direction, in both directions, there will be a transition zone, alright, where you'll talk about instead of having a very squarish one, you actually have a triangle one, alright. So normally we use a mesh with triangles to model something that is transitioning, alright. It's okay if you were to do it, but it should be avoided as much as possible. So you don't want any form of triangular to happen, alright. So, and that these transitions should be located in less critical areas, in areas that is not very concerned, alright. And therefore, for example, come to the plate with a whole system. For example, over here, as you can see, alright, this thing over here, there is triangle, alright, and as you can see, the shapes are all, although we can maintain the squarish shapes all over here, but over here there is a point where you have problems with, and your particular, this point over here is macam not like a circle, alright, because your meshes are very coarse, or are very open, or not very fine. So what we can do is actually to break this. So if I were to redraw this thing, okay, maybe I should erase this, or I should erase quite a few of this stuff, maybe a few stuff, alright. So this is the line over here, for example. I will actually break it down into this thing, alright, and I'll mesh this part first. I'll mesh all these parts, alright. So this part over here is what I've shown over here, this line. So you draw a symmetry base, you draw a slightly quadrilateral one first to model whatever thing. So as you can see, everything over here is pretty nice, alright, while the rest over here will model the quadrilateral. As you can see, the quadrilateral is getting smaller and smaller size. So the more you move towards a curvature, alright, the element gets smaller and smaller, the size will get smaller and smaller, so that you can model the system more better, more sharply, alright. So this is why over here, as you can see, all the quadrilaterals over here are pretty big. The big is okay, no problem, because it is not something this is not a critical area. It's not something that you want to look at. And therefore the most critical area is the curvature over here. So in order to model this curvature, alright, one way is that you can model by smaller elements over at this side. Alright, more finer mesh near the critical area, while further away the meshes is getting larger and larger. Alright, things like that. Alright, so this, if you think about it, this is actually a linear system. Alright, as you can see, all the quadrilateral are all straight lines. You see, they are all straight lines. So therefore, you are talking about only 4 integration points. Alright, we should go to CPS 4 and things like that. Okay, so for integration points, how it works is like this. For example, if you want to talk about, let's say I have this particular curvature, okay, if I only look at this particular edge, alright, so this is still a 4-node element, alright, but it's curvature. So if I were to look at this particular curvature, I have this thing over here. You can use integration to actually look at the area under this curve, Another method is what we use, what we call the Gauss integration. Alright, where we integrate based on where we estimate, I should say estimate, using two arbitrary points in the curve. Alright, so this method, the Gauss method, alright, uses only 2 points to determine the whole curvature. Alright, but instead of determining this curvature, because it's only 2 points, 2 points is like macam ax plus ax1 plus ax2. So if you think about it, it's actually a linear line. So therefore, what they are actually doing is actually plotting a linear line with regards to this particular curvature. Alright, the best fit line. So nonetheless, if you think about it, if you have 3 points, alright, for example, if I have 3 points all over here, then what can we do? We can actually model the curvature quite well. Alright, for example, if I have 3 points over here, for example, alright, so the equation will be something like a x squared something, I don't know, but at least you get to know that you can model the curvature using the 3 points quite well. Alright, will be more sharper. So the more integration points you have, alright, the more you can model the system more accurately using only 4 points. No need to do integration. Alright, because why they use the Gauss integration is because if you still remember, we are dealing with matrix. You still remember all are BE, BT, B transpose. These are all matrix 3 times 3, 4 times 4. You can't integrate, so therefore often they use Gauss integration, because Gauss integration no need integration at all. You just sub in the Gauss points, and then you sub in, and then you do your own stuff, if you still remember the equation. Alright, so therefore coming back to here, alright, if we have this particular shape, alright, if I have this particular shape over here, okay, and then I have 2 Gauss points over here, I can model a square like this at each side. I can have 2 Gauss points over here, I can model this square as this side, and then I have 2 Gauss points over here, I can model at this side. I have 2 Gauss points over here, I can model this thing. So it's like a quadrilateral already, but in fact it's a curvature, you see. But the the system, alright, the thing that the analysis, like SolidWorks, the ANSYS, whatever, instead of having all at this side, so over here these are all 8 points, alright, they actually move it, alright, such that it's towards the middle. Alright, so over here at this side, alright, these 2 points over here take care of this side, alright, while these 2 points over here take care of this side. It's still 2 points, but you use a slightly further distance away from the integration line. Alright, same thing, you use this 2 points to model this thing. Okay, so the more points you have, the more computational time you require. Okay, but sometimes the more, because this is only 2 points, alright, you can only measure in terms of a quadrilateral. Alright, this quadrilateral over here will actually cause what? Will actually cause shear locking. Alright, over here the angle may not be 90 degrees anymore. Alright, we want it to be 90 degrees because we want it to be as squarish as possible. So if it's not 90 degrees, then you will have, if it's not 90 degrees, you will have a certain shearing. Alright, so some shearing that is supposedly not there, but you introduce it because of you have used only 2 integration points. So these are the things that comes as a problem, a geometric problem when you model things. So therefore they will use 9 Gauss points, which is CPS 8. But CPS 8 in other words 9 Gauss points, but you requires 8 nodes. Alright, so you'll be more accurate. Or nonetheless, you can also use 8 node, alright, but you reduce the Gauss points by 1. So one side is 2, right? At first it's 3 because it's 3 Gauss point. So if I have to reduce, so if it's CPS 8R, then I'll have 2 Gauss points only. So instead of 3, I'll have only 2. So each side of this line I have 2 Gauss points. Each side of this line I'll have 2 Gauss points. Each side of this line I have 2 Gauss points. Okay, instead of 3 Gauss, instead of this thing over here, each side over here I have 3 Gauss points to measure. Although it's accurate, sometimes it is not actually quite required. So normally CPS 8R offers this method so that you can model using a lesser computational time, alright, and also less stiff for certain reason, alright, especially for CPS 4 lah. CPS 8 actually don't have any stiffness. Most likely is CPS 4, right? Because you use a straight line to model a curvature. So most likely CPS 4 has a problem. So you'll suffer more. Alright, so things like that. So these are the few things that I find it very useful to say before I forget, and that is it.